This is Stat 225, and in this video we will be discussing independence. When we talk about independence in probability, we mean that one event's occurrence doesn't affect the probability of another event. What does this look like? Well, if A and B are events that are independent, then the conditional probability of B happening, given that A happens, should be the exact same as the unconditional probability of B happening. What this means is B has the same chance of happening whether A happens or not. We can switch this around and get the same result. So again, if A and B are independent, then A given B should have the same probability as just A unconditional. So in that case, B doesn't tell me anything about whether A is going to happen. A has the same chance of happening regardless. And so if A and B are independent, both of these things will be true. But we really only need to check one of them to prove independence. To go back to an example we've seen multiple times so far, if we draw one card from a deck of cards, and we have one event Q representing that the card is a queen, and another event H representing that the card is a heart, we can ask the question, are these two events, Q and H, independent? In order to check this, we need to do a comparison of probabilities like we just talked about. So I'm going to pick one, the probability of drawing a queen, given that it's a heart. We looked at this in a previous video. If you know that a heart card was drawn from the deck, there are 13 possibilities. How many of those are queens? 1. So the probability of queen given hearts is 1 out of 13, or 0.0769. What do I need to compare this to check for independence? I need to look at the unconditional probability of just drawing a queen from the deck. Notice the order here. I just drop the condition. So I need to compare probability of queen given heart to just unconditionally probability of drawing a queen. There are 4 queens in the deck out of the 52 cards. 4 out of 52 is the exact same thing as probability of queen given hearts. It's 1/13. So since those two probabilities are the same, yes, queens and hearts are independent. And we can think of this intuitively because each suit has the same number of queens in it. So knowing the suit doesn't tell me anything about whether the card is a queen or not. Therefore, these two events are independent. And there's a little logical extension we can look at too. Knowing that the card was a heart didn't tell me anything about whether the card was a queen or not. What if I knew that it wasn't a heart? That still wouldn't tell me anything about whether it was a queen or not. And so if two events are independent, then one event's complement and the other event are independent. And it doesn't matter which complement that goes on, and in fact, it could go on both of them. So one of these statements implies all the others. To think back to a couple of tools we've looked at so far over the past few videos, we looked at the general multiplication rule, which remember was just a rearranging of the definition of conditional probability. To get the intersection of two events, I take the probability of one multiplied by the conditional probability of the other one given the first one. And as we just saw, if two events are independent, the conditional probability is the same as the unconditional probability. If I combine these two facts together, I get what's called the special multiplication rule. So if I have two independent events A and B, their intersection probability is just the product of their simple unconditional probabilities. So the probability of A intersection B is just the probability of A times the probability of B. So for an example here, we just showed that queens and hearts were independent. So if I find the probability of queens intersection hearts, I can just take the probability of each event. Probability of queens is 1 out of 13. Probability of hearts is 1 out of 4. Multiply them together, I get 1 out of 52. which is exactly what we should expect here, because only one of the 52 cards in the deck is both a queen and a heart at the same time. It's the Queen of Hearts. Here's an example that will help us practice a lot of the stuff we've been talking about. Let's say you flip 2 coins, but these coins are weighted, they are unfair. And so the probability of heads on a coin is 0.75. The first question is, are these flips independent? So does what happens on the first flip tell me anything about what's going to happen on the second flip? Let's say I got heads on the first flip. Does that change the probability of getting heads on the second flip? No, it's still 0.75. So these flips are independent. Probability of heads on the second, given heads on the first, is just the same as probability of heads on the second. Heads on the first tells me nothing helpful about the second flip. It's still 0.75. And so here I can write out the sample space. On each flip, I'm either getting heads or tails. So I could get 2 heads, or heads and then tails, or tails and then heads, or 2 tails. And I can find the probability of each of these. Now, when we did coin flip examples in the past, all of these outcomes were equally likely. Is that still the case here? No. Previously, we were dealing with a fair coin, where the probability of heads was 0.5. But now, heads is much more likely to occur than tails. And so 2 heads is going to be more likely than 2 tails. So I can't just say that each of these probabilities are 1 out of 4. I need to actually calculate them. Well, it's pretty easy to calculate them because I just said the flips are independent. So for this first outcome, heads and then heads, that's an intersection. I need to find the probability of heads on the first, and I can just multiply that by the probability of heads on the second because they're independent. Well, both of those probabilities are 0.75, so I get that the probability of heads and then heads is 0.5625. What about heads and then tails? Again, the flips are independent, so I just need to multiply 2 unconditional probabilities together. Probability of heads on a flip is 0.75, and using the complement rule, probability of tails must be 1 minus 0.75 or 0.25. So I multiply those together and I get that this probability is 0.1875. By the same logic, tails and then heads, I switch the order of multiplication, but of course it doesn't make a difference. We get the same probability for that outcome. And for the last one, 2 tails, that's just going to be 0.25 times 0.25. If you want to double check these, what should those 4 probabilities add up to? 1, and you'll see that they do. Then I define 2 events. Event A is that I get at most 1 tail. So what does it mean by at most 1 tail? It means either there is 1 tail out of the 2 flips or no tails out of the 2 flips. What outcomes are included in this event? These 3. So 0 tails or 1 tail in 2 ways. Event B is that I get at least 1 tail. So that means either 1 tail or 2 tails. That's these 3 outcomes. And so if I want to find the probability of each of these events, all I need to do is look at which outcomes are included in those events. I already have the probabilities for each outcome, so I just need to add up their probabilities. So the probability that I get at most 1 tail, probability of event A occurring, is just 0.5625 plus 0.1875 plus 0.1875 for a probability of 0.9375. And likewise for the probability of B, I add up the probabilities for the 3 outcomes that are in event B, 0.0625 plus 2 of the 0.1875s for a probability of 0.4375. Next, I will find a conditional probability, probability of B given A. So keep in mind how conditional probability works. I'm narrowing down my sample space. I know event A happened. So I'm only going to be looking at the outcomes in A, and out of those, I want to look at how likely is it that B happened. So if you remember back to our equation for conditional probability, I look at the intersection of the two. In my picture, that's pretty easy. It's where the two red circles overlap. It's those two outcomes where there is exactly one tail. So I add up those probabilities, and then I divide by the given event's probability of A, which we just found. And that gives me a probability of 0.4. And finally, I have a series of questions about the relationship between event A and event B. The first thing is, are A and B mutually exclusive? Mutually exclusive means there's no overlap between them. And we can see by my little picture or by the intersection that I just calculated, there is an overlap. They are not mutually exclusive because it is possible for both A and B to occur simultaneously. Another term we introduced was exhaustive. Are A and B exhaustive? Do they include the entire sample space? Well, yes. There are only 4 outcomes in the sample space, and I've included all 4 in at least one of these 2 events. Their union covers everything. So yes, they are exhaustive. One bonus question I don't have on this slide. Do A and B form a partition of the sample space? To be a partition, you have to be both mutually exclusive and exhaustive. A and B are just exhaustive, but not mutually exclusive, so they are not a partition. Alright, the last one here asks, are A and B independent? To check for independence, I need to compare a conditional probability to an unconditional probability. I have one conditional probability of B given A. I found that that was 0.4. What unconditional probability should I be comparing that to? I just drop the condition, I drop off the given A part, so I need to compare it to the probability of B. And since the probability of B given A is less than the probability of B, that means A does tell me something about B. B happens 43.75% of the time, but if A happens, it's less likely to happen. It only happens 40%. So A happening drags the chance of B happening down by a little bit. It's not a lot, but it does change it, and therefore A and B are dependent. They are not independent. So far, we have just talked about independence with regard to 2 events at a time. We have a couple other ways we can talk about independence when we have more than 2 events. So here, let's just keep it general. I have n events, A1, A2, A3, A4, up through AN. If all pairs, all groups of 2 I can form from those events are independent, then I say that whole group are pairwise independent. A step beyond that is mutual independence. If all possible collections, so not just pairs, but including pairs, but also groups of 3, groups of 4, up through the group of all n of them, satisfy the special multiplication rule, then I say those events are mutually independent. And so if I have a group of events that are mutually independent, that implies that they are also pairwise independent, because that's included in mutual independence. But just because I have pairwise independence for a group doesn't necessarily mean they're mutually independent. I also need to check those larger groups and see if they satisfy that special multiplication rule. Let's look at an example. So we just spent a little bit of time looking back at the events Queen and Hearts for drawing a card from a deck of cards. And one we've also talked about before is the event F for face cards. Remember, that includes Jacks, Queens, and Kings. I want to know, is that group of 3 events pairwise independent? And then also, are they mutually independent? To check for pairwise independence, I need to check each pair of those events and see if the pair is independent. The first pair is Queens and Hearts. I need to check if they are independent. We've already done that in this video, so I'm just going to double check it by doing a different comparison that I could do. I can check the probability of hearts given queens, and then see if that is the same as the unconditional probability of just drawing a heart. Another pair is hearts and face cards. I need to compare a conditional probability to an unconditional probability there to check to see if that pair is independent. And the final pair is queens and face cards. I need to do that check. So if each of these comparisons ends up to be true, then we say that this group is pairwise independent. If those three are all true, plus this last thing is true, then we say the group is mutually independent. What's this last thing? I look at the group of all three of them and check to see if it satisfies the special multiplication rule, which said to find the intersection of all these events, probability of queen and heart and face card, I multiply out their individual probabilities. Probability of queen times probability of heart times probability of a face card. If that product is the same as that three-way intersection, and those three previous comparisons all check out, then these three events are mutually independent. Alright, so I know the answer to the first one, but since I'm approaching it a different way, it's good to double check. First, I'm going to find the probability of heart given queen. So I draw a card from the deck, I tell you it's a queen, and then I ask you, given that piece of information, what's the probability that it's a heart? Well, there are only 4 queens in the deck, and how many of them are hearts? 1. So this has a probability of 1/4 or 0.25. What about unconditionally? Without knowing anything about the card, what's the probability that it's a heart? Well, there are 13 hearts in the deck out of 52. That's also 0.25. So, yes, this confirms what we saw earlier using a different comparison, but hearts and queens are independent. Cool. Next one. Hearts and face cards. You know that a card is a face card, so you know it's one of the jacks, queens, or kings, and I ask you what's the probability that it's a heart. Well, out of those 12 possible cards, there are 3 hearts. The jack of hearts, the queen of hearts, the king of hearts. So 3/12 is 0.25. And as we just saw, probability of hearts is also 0.25. So hearts and face cards are also independent. So what we've seen so far is the value of the card doesn't tell me anything about the suit of the card, and vice versa. What about this third one? Probability that I draw a queen, given that's a face card. As we just mentioned, there are 12 face cards in the deck. How many of them are queens? 4. The 4 queens. So that's a probability of 4 out of 12, or 1/3. Unconditionally, what's the probability that I draw a queen out of the deck? Well, there are 52 cards in the deck, and 4 of them are queens. That's 0.0769. Those probabilities are not the same. If I know that I drew a face card, that really narrows it down, and it increases dramatically the chance that it's a queen. So those two probabilities are not equal to each other, so queens and face cards are not independent. And since all 3 of these pairings were not independent, then I cannot say that this group is pairwise independent. Could they be mutually independent? Well, no. Mutual independence includes pairwise independence, so I really don't even need to check the last thing. If they're not pairwise independent, they can't be mutually independent. Feel free to check this last equality for yourself, but I'll just tell you right now, it does not work out anyway.